equations is start a process that actually expands into other topics. It has to do with finding a coordinate on a piece of graph paper that two graphs intersect at. That's basically all it is. And we're going to start off with simple graphs, of course. That would be linear equations. So if we're talking about linear, what are we really talking about when we say linear? A line. Oh. And when we're talking about lines, and I'm talking about two graphs intersecting each other, what are the three possibilities with lines two lines in a plane? What are the three different possibilities? Perpendicular is not really interesting in the sense of how lines lie. So one of them would be parallel. And I can see already I have to change this part. Now, if they're parallel, parallel lines, they look like this, they have the same slope. And I say, well, a system of linear equations is the intersection of graphs. But if two lines are parallel, they don't intersect. So therefore, when we talk about a system of linear equations, there is no solution because they do not intersect. So there's no point in common between these two graphs. All right, what's the other possible setup for two lines? Intersecting. And that would take care of the perpendicular because perpendicular lines intersect. Intersecting. And this is the one of interest because the two lines, just run into each other. So if you have these two lines running into each other, how many solutions do they have? One point of intersection. So when you have intersecting lines, they only share one common point. Most people don't get the third. Oh, let me write this down. One solution. Some coordinate x comma y there. What's the third possibility with two lines in the plane? It's funny that nobody gets it. Nobody? Come on.
Is it just a straight line?
What do you mean just a straight line?
I don't know. I just
You're actually on the right track. But there has to be two lines.
Two random lines, like random periods.
Well, these are random in a way. They're either intersecting or parallel, but there's one more possibility with two lines.
You said it has to be two?
Two lines that are exactly the same. You can put one line right on top of another line. So you could have two lines on top of one another. That's a possibility. I always thought of like spaghetti. You could just lay the spaghetti right on top of one another and they share everything. So how many solutions are there? Well, if this is one of your lines, and you have a line right on top of it, how many times do they intersect?
A lot.
Well, a lot. I heard the word though. Infinite solutions. Every single point is a common point. So there's an infinite number of solutions. Let's see. There's words for this. This one is inconsistent, I think. No, maybe that works with linear. There's some words for these, and I just forget what they are. I never worry about them. So what we need to do is discuss the possibilities. How do we find well, first of all, how would I know there's no solutions or infinite solutions? They actually have the same kind of setup. What has to be true if you have no solutions? Well, the two lines are parallel. So how would you determine if two lines are parallel? They would have a different y-intercept. What's the other condition?
Same slope.
Same slope. So this situation up here would be different y-intercept and same slope. This situation down here where there's infinite solutions.
It's the same y-intercept, same slope.
Same y-intercept, same slope. So you can kind of get an idea that these two I'm going to try to keep rare. I'm more interested on the ones that intersect. But these do crop up where you're talking about no solution, parallel lines, and infinite solutions, same line. All right, I'm just going to steal some problems out of the book. These are kind of impossible to make up. All right, switch out markers here. Number 6. You don't have to look in the book. I'll just copy everything down. They give you a coordinate. They give you a system. I'm going to write them next to each other. For the most part, a lot of the beginning of this topic, they write the equations over each other. That's just standard setup. To solve most of them, you need to write them side by side, so you have some room underneath both of them. If you write them over each other, you put the second equation down below this one, you have no room to work the top one. So it's better sometimes to separate them. There are some situations where we want to put them over each other, but that's the last technique that I'm going to show you today. So what the question is asking is, here's your two lines in a plane. Here's a point. Is this the point where those two lines run into each other? So how would you find out if this point is on both lines? Well, actually, take this point and just put it in. This is x, this is y, and just do a substitution. If it is a point on this line, what should happen? What happens when you check your work?
It'll be true.
Yeah, you'll get something like 5 equals 5 or 7 equals 7. And if it's false, you'll get something like -3 equals 5. It'll be an untrue statement. Now, the left one, you have a choice. You can just plug in and see what happens, which I think is the easiest way to do it. Or you can get rid of parentheses and all that fun stuff. Personally, I think just plugging a number in will work fine. So this is 2 times some number. For those people that have yet to use my idea of replacing variables with parentheses, now's the time to start doing it. Because it's going to get uglier in a little bit. What's x equal to? -4. Minus 3 times, and then we have this y here. 2/3, fraction. Minus 5. And we want to see if this thing is equal to 5. Now you can see why I separate them on left and right.
Yeah.
All right, simplify. 2 times -4, -8. What should we do here in the second portion? Distribute. So we can distribute this through, and the nice thing is, 3 times 2/3, the 3's are going to cancel out, which is rather nice. Be careful, it's -3 times 2/3, which is -2, and -3 times -5, which is +15, and we want to see if this is equal to 5. All right, 8 minus 2 is -10? Oh, that's a negative. -10 plus 15 is 5. So we get 5 equals 5, and that's a true statement. Now, if we got to something like 2 equals 5, then we could just stop right there and say this is not a point on both lines, it's not a solution. All right, the other one, much easier, 6y equals x plus 8. Do the same thing. It's going to be 6 times -4. What?
Oh,
2/3.
Sorry.
This is a y coordinate. Equals x plus 8. What goes into x? -4. So 3 goes into 6. 2 times 2. So we get 4 on that side. -4 plus 8 is 4. So we can say yes, -4 2/3 is a solution. In other words, it is a point on both of these lines. It is their point of intersection. Not that bad, right? That's kind of easy. Except, I know how you all are with sign mistakes and calculation error. That's going to hold you back on some of these, so be careful. Now, the other possibility is you have to go looking for the solution. That's more common. That's pretty much just how you check your solutions. Once you find a solution, you can plug it into both equations, and it has to work for both of them. Now, if we're talking about finding a solution, there's a couple techniques that work decently. This is number 8 out of the book. 3x plus y is equal to 5. 2x minus y is equal to 5. Again, notice I'm writing them side by side rather than the way that the book writes it over each other. What should I do? Well, this one I want to graph to solve. I we're going to have to be very careful how we do this. It should work out rather well. Well, if I'm going to graph to solve, what do I need to do to both equations? Solve for y. This one's easy. This is y equals negative 3x plus 5. This one requires 2 steps. Negative y equals negative 2x plus 5. Then what? Go through and change everything sign-wise. This is positive 2x and negative 5. All right. Are they parallel? I mean, if they're parallel, you don't have to go any further. No. This one has a slope of negative 3. This one has a slope of 2. The y-intercepts are different. So let's just graph it. Let's see how cautious we have to be. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2. Hopefully I made these marks somewhat equidistant. This section you really might, I'll print off some graph paper. You might want to go to my website and go to the 161 page and print off some graph paper for yourself. 1 or 2 sheets should do you fine. Probably just 1. I have a couple up here. I don't think I have enough though. So let's graph this one. Here's a problem. This one is y, and this one is also y. This is a good place to use what kind of notation? What can I replace y with? F of x and g of x. Why not? So let's call this one f of x so I can label it properly in the picture. And let's call this one g of x. Function notation is wonderful for separating away 2 equations that are both y equals. All right, so let's do f of x first. F of x is y-intercept. 5, 0, 5. So you go up 5. You plot your point. And the slope is negative 3, but you want to think of it as negative 3 over 1. So from that point, you want to go down 3 and right 1. So right about here. And then you also want to go down 3 again and right 1. And we're going to do a bunch of these. Down 3 and right 1. And we get this nice line, supposedly. And this is why graph paper comes in very handy for this piece. All right, g of x, I'll do this in red. G of x has a y-intercept of 0, negative 5, so we come down here. And the slope is up 2 over 1, up 2 over 1. And we can draw this line, kind of crooked, but you get the idea. What happened? Well, the red slope points ran into the, I'm sorry, did I just say red and I followed my finger on the green? The red slope points ran into the green slope points right there. What is the coordinate of that point? 2, negative 1. So the solution to the system is 2, negative 1. And that's it. Usually with these, the slope points are going to run into each other. If they don't, it gets a little messier and you actually have to find the coordinate of intersection. What's wrong with this method? Technically, it always works, but what could cause some difficulties?
You don't know where it intersect. It might not intersect on the number graph we have, like the numbers are really high.
Yeah, the grid. It might intersect, like, if this is your grid, your points might intersect here, your 2 lines. What coordinate would that be? Well, it's a little bit of this and a little bit of that. It would be decimals or rational or something silly like that. So there's got to be better techniques to come up with an intersection. Graphing is just a pictorial view of it all. Gets us started. The next method is probably one of the more nasty ones. The only thing good about substitution is it works for other types of system of equations, ones that are not linear. Quadratic, cubic, circular, elliptical, all different types of ones will work with substitution. Lines have a special type of solving. There's actually two different ones that are very nice, but they only work for lines. Substitution works for everybody. So works for all types of systems. Substitution is actually the main way of solving a system of equations. Linears just have a nice shortcut that the other systems sometimes don't have. So for instance, number 16, start off nice and easy. Again, I highly suggest you write them next to each other for now. There is one type that we're going to do today that we write them over each other. But that'll come later. For now, if you're doing substitution or graphing, or if you have to do some work underneath each of the equations, side by side is a better way to start. All right, if we're going to do substitution, it pretty much works out this way. Let's put it over here. One, solve one equation for one of the variables. Now, how should you choose that one equation? Whichever is the easiest one to solve. Like, for instance, if you have to solve for x here, you're eventually going to have to divide by 2. You're going to get a fraction here and a fraction there. That's not nice. If you solve for y here, you eventually have to divide by -5. You'll get a fraction here and a fraction there. So I wouldn't even touch this equation unless, something bad happens over here. But if I solve for this x, life becomes kind of easy. All I have to do is move the 3y across and I'm done. So the first step is you want to solve for one equation for one of the variables. Technically, it doesn't matter which one you do, but usually you want to choose the easiest one. So choose easiest, if possible. Only if it's possible. If it's not possible, just pick one and run it through. Second step, let's do it. Plug this solution into, and this is important, other equation. The biggest problem I've ever seen with systems of equations substitution method is a student will solve one of the equations for one of the variables and plug that solution back into the same equation. If you do that, your answer is going to be 0 equals 0, which gets you absolutely, well, nowhere. So your goal is, if I choose number 2 over here to solve for, I plug it into number 1. Plug it into the first equation, and that's what I'm going to do. So if I solve this equation for x, we're going to get x equals 3y minus 3. Now substitution allows me to say, well, if x is equal to 3y minus 3, I can take every x and replace it with 3y minus 3. It's technically the transitive property. So what I'm going to do is I want to plug it into the other equation. So you're going to go 2 and a big parentheses. Remember those parentheses I've been warning you about? They get worse. So it's 2 times something minus 5y is equal to -1. I highly suggest you write it this way. What happens is this. You start focusing on the 3y minus 3, you write in 2 times 3y minus 3, and you forget the 5y. So get the format of it down first, and then go back and plug in what it's equal to. In this case, 3y minus 3. Just trying to reduce the mistakes that do get made. After a while, you start getting used to it, and you start forgetting little pieces. All right, so what should be our next step? Solve this. We're only down to one variable. Solve linear in 1 bar. So we're going to solve that equation for the variable y. How do I solve it for y? Distribute. So we get, what, 6y minus 6 minus 5y is equal to -1. After you distribute, your next step should be combine like terms. So 6y minus 5y, what property allows me to do that? Yes, we're not done with them. I love going back to them. So how do I get 6y minus 5y to come together?
Right, and the
What was it? No. No. Nope, there's no parentheses here. When you switch orders, it is called commutative.
I said.
I didn't hear you, I'm sorry. Talk to this.
Right.
So 6y minus 5y is 1y. What property allows you to go from 1y to y?
What?
inverse.
Nope.
What is that?
Identity. So we get y minus 6 is equal to negative 1. You're going to have it on the final. You might as well practice it. Switch order, commutative. 1 times y is identity.
We'll do it on the
Huh?
Just skip the review.
Oh, we'll skip to the review now. So how do I solve for y? What property? Additive inverse. So you get y is equal to 5. Everybody's not going to do it. Is that a property? Actually, it is, but let me give you a hint. If you ever say the word cancel, there's 2 properties that go in a row. Inverse is first and identity is second. So when you say the word they cancel, it's inverse and identity. Just a hint. All right, now that you have y is equal to 5, the last step is plug answer. It doesn't matter, really. Into either equation. Which one should you pick? The easier one. And usually what the easier one is this. You solve this one for x. So if I take y is equal to 5 and I plug it into there, notice this big circle that just happened. You went from over here, you brought it over here, you solved it, now you're going back to here. But you don't have to plug it into here. You could plug it into the equation you already substituted into. It doesn't matter. So you take the 5, you plug it in here. 3 times 5 is? 15 minus 3 is?
20.
So we're going to get x is equal to 12. So how do I write my solution? This is important. If you leave this on your test paper like this, even though you have the right values, you lose a point. So how do you write a solution? Well, the solution is it's a point, it's a coordinate. Comma, 5. And there's your solution. You have to write it as a coordinate because that's literally what it is. It is a coordinate on a piece of graph paper. Just like that y-intercept thing. That's not that bad, right? It's all right. One thing that made it all right is, well, one of the equations was really easy to solve for, and there are absolutely no fractions. No, it'll be nice and ugly fractions. But they're not hard to deal with. You know how to deal with them already.
Mr. Kalar, how you get to that second step, x equals 3y minus 3?
Here,
You solve for
I
x.
solved for this one for x.
Okay.
You just add 3y to both sides. And you get 3y minus 3. It's easy. You've been doing this, for 2 chapters now. So you should be like, this is easy. All right, now I'm going to go away from the book and I'm going to make up one. Now what happens when you make up one is things don't turn out to be nice. So here's just an example. 2x minus 3y is equal to 7, and 4x plus 5y is equal to negative 8.
No solution.
Yeah, it has a solution. They are not parallel, I'll tell you that. Definitely not parallel. So I've set this up so things are not so, nice, sad. But if you look at this one, if you divide by 2, how many fractions do you end up with? 2 of them. Divide by 3. 2 fractions. Divide by 4. 1. Guess which one we're solving for? This one here.
Yeah.
Because if we divide by 5, again, we end up with 2 fractions. So by just looking at some of them, you can figure out which one's the best one to solve for, the least fraction. Sometimes you don't get that choice, but this one's nice. So we're going to solve for this x. This will be our first step. We're going to solve for that x, get it by itself, and then we're going to plug it into the other equation. So if we solve for x, we're going to get 4x is equal to, careful, negative 5y minus 8. And finally, divide by 4 and you get x equals negative 5 fourths y minus 2. So we're going to take this equation and we're going to plug it into the first one. We're not always going to be solving the second one. It just happened to be in this case. It really doesn't matter which variable you solve for either, but I like the one with the nicest one. So when I plug it into this other equation, you're going to replace the x with parentheses first, because we're substituting away the x. So this is going to become 2 times something minus 3y is equal to 7. 2 times something. Now what's that something? Negative 5 fourths y minus 2. And then we have a nice equation in one variable. Nice linear one. What should I do first? Distribute. So we're going to get, better known as 10 fourths, 5 over 2. So this is negative 5 halves y minus 4 minus 3y equals 7. All right, next step. Great, except for one thing. I'd get rid of the fraction, personally. Unless you could do fractions really nice, I'd rather get rid of them. Keep the mistake out of there. So what do I multiply by? 2. So take this entire side, multiply it by 2. Same thing for the other side. Whatever you do to the one side, you have to do to the entire other side. Distribute the 2 through. It turns out rather nice. 2 times negative 5 halves. Negative 5y, 2 times negative 4, minus 8, 2 times negative 3y is equal to nice integers. All right, next step. Combine like terms, the 6 and the 5 become negative 11y. What property? Commutative with a mixture of? What property is like terms? I know, and I'm bringing it back to your memory. How do you combine like terms? You know,
Is that different?
3x plus 4x equals, what did you ignore? The x. So where did it have to go? Well, outside. What pulls an x outside? Distributive property. When you're combining like terms, it's a distributive property. Minus 8 equals 14. Shortcuts. Gotta love them. Next, what's up? Add 8 to both sides. You're going to get negative 11y is equal to 22. Oh, you gotta be kidding me. I made up a problem and the answers are actually going to come out nice. I didn't want that. Divide by negative 11 and you get y equals? Ah, come on, what is the probability of me getting one that comes out integers? I didn't mean on that. Oh, actually, not all of it's integers though. So y equals negative 2. Then you just, what's that? It's part of the answer. Oh, fine. Take the negative 2 now and plug it into that equation. That seems the best pattern. All right, if we plug it into that equation, we're going to get x equals negative 5 fourths times something minus 2. And that something happens to be negative 2. And simplify. Negative 5 fourths times negative 2. It's 10 fourths, and it's going to be positive. And 10 fourths is better known as 5 halves minus 2. Now your choice. You can either work with the fractions, just get an answer, which is a little bit easier, or you can multiply everything by 2, solve for x, but I think that'll take too long. The common denominator here is 2, so this is 5/2 minus, multiply the bottom by 2, top by 2, so this becomes 4/2. And therefore x is equal to 1/2. So the final solution, which I can put a box around, is x equals 1/2, y equals -2. And that is where these two lines intersect. I was hoping for like 17, 13, -25, 19, something ugly. It didn't show up. But that's substitution. And that works for all types of linear equations. The problem with it is there's a lot of solving going on, a lot of places for mistakes. It takes up a lot of, well, room on a piece of paper. It takes some time to get through all that. So there's got to be a better way of doing it. The other way of doing it, what time is it? Oh, we have plenty of time. It's called elimination. Or at least, that's what I call it. What's the book called? They call it, well, addition elimination method. They call it the addition method. Personally, I like elimination because it tells you what you're supposed to do. You're supposed to eliminate something, get rid of something. In other words, we're going to remove a variable. From both equations. What's nice about this method is you generally can avoid fractions, working with fractions. You might have answers that are fractions, but technically you can avoid working with fractions at all throughout a problem. Oh, let's see. That one's nice and easy. Number 24. Let's see. 12x minus 5y is equal to -7. 4x plus 2y is equal to 5. Notice what I did different already. Usually I wrote them side by side. If you're going to do the elimination method, you have to write them over each other. The second thing that has to be true is they both have to be in standard form. That ax plus by is equal to c for this method to work. They have to be in standard form. So if you have an equation where x and y are on both sides of the equation and you want to use elimination, you have to shift them both to the same side. Usually the left is where they go. So they have to be in standard form. You want your x's to line up, you want your y's to line up, you want your equal signs to line up, and you want your numbers, your values to line up. By the way, those are not y-intercepts. Just because they're by themselves, it's not the y-intercept. So here's the technique. Pick a variable that you want to get rid of. Just pick one, I don't care which. Let's get rid of y. So once you choose to get rid of or remove the y value from contention, the way you're going to do it is additive inverses. So here we have a -5y and a +2y. If we're going to use additive inverses, we want those y's to be the same value, opposite signs. One positive and the other one negative. What's that? We're going to multiply the entire equation by 2 on the top and the bottom by 5. What happens here is 2 times -5y is -10y. +5 times 2y is +10y. There's your additive inverse. What allows me to do this? Well, it's a distributive property. It's also that idea of whatever you do to the left, you do the same thing to the right. Where's the most common mistake for this type of problem? Do you want to know? not multiplying him by 2, and not multiplying him by 5. Those numbers on the right also have to be hit. You can't just do the left and ignore the right. Whatever you do to the left, you do to the right. And notice how I have these parentheses set up. Instead of doing both sides the legal way, I have a shortcut way. I put the parentheses around the whole thing. That means it distributes over the whole thing, which will take care of the left and the right. So it's kind of like a shorthand notation. All right, so if we distribute the 2, we're going to get 24x. Highly suggest you leave a space here. Why? You're going to have so many equations all over the place. You want to keep the 2 that you're working with grouped nicely. So we're going to get 24x minus 10y is equal to negative 14. Just don't forget that 7. And the second equation is going to be 20x plus 10y equals 25. Now here's part of it that is a little strange. This is actually called linear algebra, but I can't tell you why it works. It just, for your purposes, does. Why it works becomes a little bit more complex, and I don't want to get into that. We're going to take the 2 equations and add them together. Why not? See what happens. So if we add them together, 24x plus 20x is?
44x.
What? I thought you said y. I'm like, what? 44x. What happens to the y's? What property? Inverse, then identity. Inverse, then identity. Equals 11. Okay. Take the solve for x. If you divide by 44, 1/4. All right. Now, you have a choice. Choice number 1. You can take this answer and plug it into either of the original equations. Don't plug it in anywhere down here where you made your changes. Go back to the originals. So you can put 1/4 back into the originals, which wouldn't be too bad in this case. Or, this is what I usually do, we first chose to remove the y. You can always then choose to remove the x, do the same process, and you never ever have to work with fractions. Which one do you want to do? Let's just plug it in. So we're going to take the 1/4 and I'm going to plug it into one of the equations. The bottom one looks nicer. Why does it look nicer? Well, the numbers are smaller. So take 1/4, plug it into this equation, which is from right here, and see what happens. So we're going to get 4 times, we're substituting the x. And what are we substituting in for x? 1/4. And 4 times a 4th comes out nice. 1. What property? Which one? It's inverse. Which one? Multiplicative. Right. So this becomes 1 plus 2y. Hey, are you getting a hint that I might be putting these on the next test? Just for fun. I know that. They're 2 different things. All right, how do you solve for y? Subtract 1 from both sides. You get 2y equals 4, and y equals 2. So the solution to this is 1/4 for the x, 2 for the y box. I highly suggest in this case you do box your answers. Because notice what happens. This whole thing is an absolute mess. The box will bring your answer out into clear focus. That one's not even that neat. So let me make up an elimination one that is not so friendly, hopefully. With my luck, I'll come up with something nice and easy. The book ones generally come out nice. 3x minus 5y is equal to -1. 2x minus 8y is equal to 7. I'm curious. will this work? It's just a plain old example for me. Now the nice ones are if one of the variables has like a 1y or a 1x, that'll make life easy. The best ones are that you have the same number for the x's, just the opposite sign, or same sign, and you have to change a sign. Some of them turn out to be really easy. This one's not. So which variable do you want to get rid of? X. That seems like the easier one. So what can I multiply the top by? Why would you want to put the negative up top? I like it on the bottom, but that's me. -2. Fine. What do you want to multiply the bottom one by? 3. Okay.
Where we get that -2 from?
What do you mean, where do we get it? We chose to get rid of the x's. I need them to be the same number. What is the same number I can multiply up to?
Oh, okay.
6, right? I'm going to choose one of them to be negative and the other one to be positive, to force one to be negative and the other one to be positive. Now be careful. Over here we multiply top and bottom by positive. But over here we have to change the sign, so one of them has to be a negative. Personally, I like putting the negative on the bottom. All right, so distribute them through, and you get -2 times 3x, -6x, -2 times -5y, plus 10y, -2 times -1, don't forget him. Something's wrong with someone's voice back there. Distribute the 3 and you get 6x minus 24y equals 21. And add them together. And see what happens. What should happen is the 6 cancel. Inverse identity type thing. 10y minus 24y, -14y is equal to 23. Oh, yeah, this is my type of problem. If we solve for y, we're going to get -23/14. Beautiful number. It's gorgeous. Now, I highly suggest we don't do it like we did this one over here. Because then you have to take in 23/14, plug it into one of these original equations, and come up with something absolutely horrendous. So my suggestion is, go back to the beginning. We got rid of the x's the first time around. Let's get rid of the y's the second time around and see what happens. What can I multiply the top by to get rid of the y's? 8? Doesn't matter. 8. What's the bottom one? -5. So I'm going to multiply the second round to see if I can get rid of the y's. So if you distribute the 8, 3 times 8 is 24x minus 40y equals -8. Make sure you get your signs correct. Now this is -5 times 2x, -10x. -5 times -8 is positive 40y, which is good because these are additive inverses. And -5 times 7 is -35. And take these two and add them together. And it eliminates the y's. So 24x minus 10y. What's cool is this turned out to be 14x. This one turned out to be 14y. They become sometimes the same number. Very common. Is equal to -43. And divide both sides by 14 and you get x is equal to -43/14. So by doing both of them, eliminating the x's and then eliminating the y's, we didn't have to work with fractions through the whole process until we got to the answers, which is actually kind of nice. So the final solution, where these two lines are going to cross, very ugly, make sure you get it in order, x comma y. So it's -43/14 and -23/14.
What's your box? Your answer doesn't stand out.
What's that?
Your answer doesn't stand out.
Better? You gonna become a teacher or something? Take my job, please.
Oh, not
Please.
bad.
I'm always trying to find someone to replace me.
Are we done?
Are we done? Are we ever done? Yeah, we're done. Let's see.
Do you come up with the questions on the text?
Yes.
I don't think
Why?
you do that.
Oh, do you find them difficult?
Yes.
Difficult.